This is the fourth section of chapter 7, the simplex algorithm, and this is about the two-stage simplex method. Now, when do we use the two-stage simplex method? Well, it's used when we have greater than or equal to in our constraints. You would have seen previously in section 7.2 when we had constraints that were all less than or equal to, and then we can just use the simplex method straight off. But as soon as we introduce any greater than or equal to constraint, we have to use this two-stage simplex method. Okay, now first we need to note is that slack variables now become surplus variables. So when we have less than or equal to in our constraint, we have slack variables, so we add the slack variables on. When we have greater than or equal to, we have now surplus variables, and these get subtracted from the inequality to make it become an equation. Now, since we are subtracting a variable here, we could end up with this variable having a negative value. And we know from the work we've done before, slack variables need to be positive and surplus variables need to be positive. So to avoid surplus variables becoming negative or being negative, we need to add on what we call an artificial variable. So in our process of turning our greater than or equal to constraints into equations, we need to add on an artificial variable ABC. Now you can see if we just use RST ABC, we're going to get lots of different letters. So to make things a little bit clearer, we will call our artificial variables A1, A2 and A3, and our slack variables, rather than R, S and T, we will call them S1, S2, S3. So once we've set up our constraints and our objective function, we're now ready to apply the algorithm. So we would have got our objective function and constraints into what we call standard form. The next step is to create a temporary objective function, which we'll call I, to minimize the artificial variables, to minimize the sum of the artificial variables. So this will be our temporary objective, minimize I, which is the sum of these artificial variables. Now we know that when we apply the simplex algorithm, then what we would do is to multiply this by -1, so it becomes a maximizing problem. So this will be maximizing the negative sum of the artificial variables. The next step would be to construct our tableau, apply the simplex algorithm to get I equal to 0. And if I does not equal 0, then there is no feasible solution. Now, these steps here is what we call the first stage or the first phase of the simplex method. The last step is to remove the artificial variables from the tableau and apply the simplex algorithm again to get our final solution, and this is called the second stage of this simplex method. Example 14, use surplus and artificial variables to write the following inequalities as equations. Okay, so we're going to need a surplus variable anyway, because it's an inequality, but because it's greater than or equal to, we also need an artificial variable. So we subtract the surplus variable because it's greater than or equal to, and we also add an artificial variable. So now we can write equal to 7. We take the second inequality, we'll do the same thing. So we'll have 4x plus 5y minus 3z. We need to subtract a second artificial variable, surplus variable, and add a second artificial variable. So now that becomes that second equation. Example 15. So we want to maximize this objective function subject to these constraints. Now, whenever we have greater than or equal to, which we have in these two constraints here, we need to make sure that we introduce a surplus variable. So that's going to be put it in minus S1 or S2 or so on, and also an artificial variable. So we need to make sure that we add A1, A2 and so on. Whereas the less than or equal to, we just add the slack variable as we would normally do. And where we have any objective functions, we rewrite those as P with some sort of function equals 0. So let's start with our equations. So we've got x plus y plus 2z plus S1 slack variable equals 10. Second equation, 2x minus 3y plus z. Now we subtract a surplus variable and add an artificial variable equal to 5. And then last equation, x plus y. And then here we also need to add or subtract a surplus variable, so that'll be S3, and add an artificial variable A2, and that will be equal to 8. Now we'll take this objective function here and we'll write it as P minus 3x plus 2y minus z equals 0. And these types of problems come in two stages, and stage 1, the first stage, is going to be to minimize the sum of the artificial variables, and they are A1 and A2. So what stage 1 is to minimize the sum of the artificial variables. In this case, it's A1 and A2. So it's a sum, so I need to put a plus sign there as well. So what we'll do, we'll call the sum of the artificial variables A1 and A2. And what we want to do is to minimize the sum of A1 and A2. Now, whenever we do a simplex algorithm, it's always to do with maximizing an objective. So we're going to maximize actually negative I equals A1 plus A2. Remember, we can turn a minimize into maximizing by changing this to a negative. So if I have a negative I here, that's the same as maximizing I equals negative A1 plus A2. Now what we're going to do is we're going to write I in terms of the other variables I've got here. So I'm going to take these two equations and I'm going to rewrite them to make A1 and A2 the subject. So I've got A1 equals 5 minus 2x plus 3y minus z plus S2, and A2 is equal to, I suppose, put little asterisks here so you know where these have come from. A2 is equal to 8 minus x minus y plus S3. So now the question becomes maximizing I, which is equal to negative A1 plus A2, so that's 5 plus 8, which is 13. Negative 2x plus negative x, which is going to be negative 3x. Then 3y plus negative y, so that's going to be 2y. Then we've got nothing else to add to the negative x, and nothing else to add to S2 or S3. Now remember, we need to write this in a similar way as we wrote this here. So we need to rearrange it so it's all equal to 0. So it now becomes maximizing I minus 3x plus 2y minus z plus S2 plus S3. So I should have written S3 here. S3 equals negative 13. And the last thing we'll do before we start using the Tableau is to declare that all our variables are greater than or equal to 0, they're all positive. So we'll just write down here x, y, z, s1, s2, s3, a1 and a2 are all positive, greater than or equal to 0. So we'll now transfer all of the variables into our tableau. So we've got x, y, z, s1, s2, s3, a1, a2. Then we have p, I, their values, and theta when we work out that ratio to decide on the pivot row. So all we do now is to transfer the coefficients. So starting with the first equation here, we will have 1, 1, 2, 1, all zeros here, and a value of 10. Second equation here, the values are going to be 2, negative 3, 1, 0, negative 1, 0, 1, and then zeros until we get to a value of 5. Next equation here, the one that starts x plus y, so that's going to be 1, 1, and then negative 1 where s3 is, and a 1 where a2 is, and then a value of 8. Now, what I'm going to put in this row is maximizing the P objective. So that's going to go in this row, and the bottom row is going to be the I objective, because that's the one that I need to minimize first. And the one that I need to minimize first, I'm going to put on the bottom row. So P is going to go here. So P, when we rewrote it, was negative 3x plus 2y minus z, no artificial slack or surplus variables, a 1 here and a value of 0. And then we'll move on to our I, and we look at this down here. So I can see negative 3 for x, 2 for y, negative 1 for z. The slack variables, surplus variables are s2 and s3, no artificial variables, no p, and it has a value of negative 13. Now, just like before, we look for the greatest negative value in the bottom row to find the pivot column, and this is the pivot column here. We're going to work out the ratio. In other words, we're going to do this value divided by this coefficient here. So 10 divided by 1 is going to give us 10. 5 divided by 2, 2.5. 8 divided by 1 is 8. So this row wins. So here's my pivot value here of 2. So now I divide everything in this row by 2, row number 2. So that will give me 1, negative 3 over 2, a half, 0, negative a half, 0, a half, 0, 0, 0, 5 over 2. Let's just move those down a row because obviously I've got my heading to put in. Okay, so this is my new row 2, and I need to write down how I'm going to get my new row 1, 3, 4 and 5. Okay, so remember what we need to do is we need to get all of these values made to 0. So since I've made this coefficient 1 from the old row 1, which will write here, I just want to take away row 2. I've got a 1 here, so with the old row 3, I want to take away row 2. I've got negative 3's here, so I want to add 3 lots of row 2 to both of those rows. So row 4, I want to add 3 lots of row 2, and also row 5, add 3 lots of row 2. So let's now work out what those values are. So we'll get 0 here, 5 over 2, 3 over 2, 1, a half, 0, negative a half, 0. These will both be 0 here, and the value of 15 over 2. Now we'll work out what row 3 is going to be once we take away the new row 2 away from it. And we'll get 0, 5 over 2, negative a half, 0, a half, negative 1, minus a half, 1, 0, 0, and 11 over 2. Then this row, which represents the objective function maximizing p, we will get these values: 0, minus 5 over 2, a half, 0, negative 3 over 2, 0, 3 over 2, 0, and then a 1 here. Remember, that's the objective function for p, 0, and then we get a value of 15 over 2. And then the bottom row here, I suppose we could put a 1 here straight away, because we know that's going to be this objective function for I, and we'll have 0, minus 5 over 2, a half, 0, negative a half, 1, 3 over 2, 0, 0 here for p, and negative 11 over 2. So now we're going to identify the pivot before moving on to the next tableau. So the most negative value we have, now remember we're minimizing I, so, or maximizing I, so we look at this row, not this row here, but the most negative value is the negative 5 over 2, so this is our pivot column. Let's now calculate the value divided by the coefficient here. So 15 over 2 divided by 5 over 2 gives us 3. So put 3 here. Now we could work this one out, 5 over 2 divided by negative 3 over 2, but we know that we ignore the negative values. So I'll just put a dash there just to show it's negative. That's not going to tell us what the pivot row is, so it's definitely not going to be this row, so there's no point in calculating it if you know it's going to be a negative. The next one is going to be 11 over 2 divided by 5 over 2, and that gives 11 over 5, which is the same as 2 and a fifth. So that means this one has 1. Here's our pivot row here, so our pivot value is going to be this 5 over 2. I'll write it at the side, it may not be clear there. So pivot value 5 over 2. So just as we normally do, we want to get this coefficient equal to 1, which means dividing this row. So we might write the row operation here. We're going to take this row 3 and we're going to divide it by 2 over 5 or times it. Let's write it as divide by 5 over 2. That's the same as timesing by 2 over 5. So we can now work out what our new row 3 is going to be. And those values are going to be 0, 1, minus a fifth, 0, 1 fifth, minus 2 fifths, minus a fifth, 2 fifths, then 0 here and 0 here, and then a value of 11 over 5. So now we can do our row operations. So how are we going to get our new row 1? Well, we'll take the old row 1 and we'll subtract 5 over 2 times row 3. So let's just write down that this is row 3 here. So subtract 5 over 2 times by row 3. To get our new row 2, we'll take the old row 2, and we've got minus 3 over 2 here. Maybe not so clear, so maybe I'll take some of these lines out. There we go, just to make it clearer. Let's just highlight the pivot value. So yeah, that was minus 3 over 2. So we're going to add 3 over 2 lots. Let's get the right colour. Add 3 over 2 lots of row 3. Then for row 4, to get our new row 4, we'll take the old row 4 here, and we're going to add 5 over 2 lots of row 3. And then to get our new row 5, we'll take the old row 5, and we'll also do the same thing, add 5 over 2 lots of row 3. So after carrying out those row operations, let's fill in what we get in the table. So we'll start with the first row, and we'll end up with 0, 0, 2, 1, 0, 1, 0, negative 1, and then 0, 0, and then we get a value of 2. In the second row, we will have 1, 0, 1/5, then 0, negative 1/5, negative 3/5, 1/5, 3/5, and then 0, 0, and a value of 29 over 5. Then we move down here to our objective rows. So this is the objective P that's going to go in this row here. And the values we're going to get after doing the row operations here will be 0, 0, 0, 0, then negative 1, negative 1, then 1 and 1 for the artificial variables, 1 here, 0 here, and a value of 13. And then our objective row for I, those values, well, we've got a whole load of zeros here. Only the artificial variables are 1, I is 1, and we get a value of 0. So notice here we've got no negatives in the bottom row. So we've finished our optimization. So we'll just put since there are no negatives in the bottom row, the optimization is complete. Optimization is complete. And is there an optimal solution in the feasible region? Yes, because the value of I is 0. Yeah, so there's only a 1 in this column, and you go down to that row, read off its value, it's 0. So we can say that since I equals 0, there is a feasible solution. Now that completes stage 1. Now to go on to stage 2, since we've completed the optimization of I, we now can cross out or delete the column with the artificial variables and I, and when we proceed to stage 2, we proceed as we would normally, as if it were a one-stage simplex algorithm question. So I'm now going to redraw this table, but take out these columns that we no longer need. So continue with this question. You can see that I've removed the columns where I had the artificial variables and the optimization of I, and also I removed the row for I as well, because I've finished with the optimization. So now this looks pretty much like any type of previous question we may have attempted. So we're just going to write down what our values are just before we start stage 2. So actually we'll write at stage 2, what do we have? We can read off those values. There's a 1 in this column. X is 29 over 5. then there's a single 1 in this column, so y is 11 over 5. There's a 1 in this column, so S1 is equal to 2. And remember, any other columns that we have that don't just have a single 1 in them, so Z, S2 and S3, their values are all going to be 0. So Z, S1 and S2 are all equal to 0. So we look for negatives in the bottom row. Now these both are the same value, so we can pick either one of these as the pivot. So I will choose this column here as my pivot, then work out the ratio, in other words the value here divided by this coefficient. So 2 divided by 0 is going to be infinite. The next row down is going to give us a negative, so I'll just put a dash there. And then 11 over 5 divided by a fifth is 11. Okay, so that tells me that 1/5 is going to be my pivot value. So we're going to take everything in row 3 here, and we're going to divide it by a fifth. So 1/3 gets divided by a fifth. So our new row 3 becomes 0, 5, -1, 0, 1, -2, 0, and 11. So we'll just write down our row 3 here. So what are we going to do with the old row 1? Well, we don't need to do anything because in that column there's already a 0, so we'll just put down here no change. So in fact we could write those values in straight away: 0, 0, 2, 1, 0, 1, 0, 2. With this value here, we're going to add 1/5 of row 3. So from our old row 2, we'll add 1/5 of row 3. Then for our old row 4, this bottom row down here, with row 4, we are just going to add row 3. We're basically going to add a 1 to that to make it 0. So we'll add row 3. So in row 2, once we've done our operations, we'll now get 1, 1, 0, 0, 0, -1, 0, and a value of 8. And in our new row 4, once we've done our operations, we'll have 0, 5, -1, 0, 0, -3, 1, and a value of 24. So now we'll find our pivot. The most negative value is -3. So this is my pivot column. I will work out these values here. So I'll do 2 divided by 1, which is 2. 8 divided by -1, well, that's negative. And this row is also going to be negative as well. So that means that my pivot value is 1 here. Now, since that pivot value is a 1 anyway, dividing these by 1 isn't going to change them. So we can just copy those straight down once we've put the headings in. So there they are, they're copied in. Now we just need to work out what the row operations are going to be. So this is my row 1. So to make this equal to a 0, all I'm going to do is from my row 2, I will add row 1. Here I'm going to add 2 lots of row 1. So row 3, add 2 lots of R1. And down at the bottom here in row 4, I'm going to add 3 lots of row 1. So let's have a look at what row 2 becomes once we do those operations. So I'll have 1, 1, 2, 1, 0, 0, 0, 10. In row 3, again, we'll look at what we get once we've done those row operations. I'll have 0, 5, 3, 2, 1, 0, 0, 15. And in our objective row down at the bottom here, again, once we've done those operations, once we've added 3 lots of row 1, we will have 0, 5, 5, 3, 0, 0, 1, 30. So now you can see there are no negatives in the bottom row. So we've reached an optimal solution. So now we can just read off the table. So x, there's a 1 in this column, and if you read that off, x is 10. Y is going to be 0. We'll do with all the ones that are 0 at the end. S2 is going to be 15. So S2 equals 15. There's a 1 in this column here. So S3 is 2. S3 is equal to 2. And our other variables before we go on to the value of P. So Y, Z, and S1 are all going to be equal to 0. So we'll just put that down. So Y, Z, and S1, S1 are all going to be equal to 0. And we've maximized P, and the value of P, again, if we just read it off, is going to be 30. P equals 30. Example 16, it says verify that the following linear programming problem has no feasible solution. So that's about showing that I is not equal to 0 once we try and optimize it. So let's get all our expressions into the standard form. So our first constraint will become x plus y plus 2z plus a slack variable is equal to 8. Then 2x minus 3y plus z minus a surplus variable plus a1 is equal to 5. And then x plus y minus another surplus variable plus a2 is equal to 10. Now we need to minimize the sum of the artificial variables, which is the same as maximizing the sum of the negative artificial variables. So now we will take these equations here, well, it's going to be these two, and make a1 and a2 the subject. So a1 is equal to 5 minus 2x plus 3y minus z plus s2, and a2 is equal to 10 minus x minus y plus s3. So we can then write that actually we're trying to maximize I equal to negative a1 plus a2. So that would be 15. Actually, let's put the negative in. Minus, and in brackets, a1 plus a2, so that's 15 minus 3x plus 2y minus z plus s2 plus s3. So we need to rewrite that. So it's all equal to 0, so, or equal to a value as an equation. So it'll be I minus 3x plus 2y minus z plus s2 and s3 is equal to negative 15. So now we're ready to put our variables into our table. Oh, and I suppose we should also declare that all our variables x, y, z. Now variables do we have? S1, S2, S3, and A1 and A2. Just about got enough space, are all greater than or equal to 0. So then I know what to put in the table: X, Y, Z, S1, S2, S3, A1, A2. Then I will put I, its value here, and then the ratio theta there in that column. So let's put the coefficients in. So starting with this equation here, we will have 1, 1, 2, 1, 0, 0, 0, 0, 0, and it's got a value of 8. On to this equation here, we will have 2, minus 3, 1, no S1, negative 1, S2, no S3, we've got an A1, no I, and a value of 5. Third equation here, we're going to have X plus Y, no Z, no S1 or S2, a minus S3, then an A2, no I, and that has a value of 10. And then lastly, we'll add this in. So we've got minus 3x plus 2y minus z. We have an S2 and an S3, no A1 and A2. We have an I, and its value is negative 15. Okay, so our pivot column is here. Let's do the calculations. 8 divided by 1 is 8. 5 divided by 2, 2.5. 10 divided by 1 is 10. So that means here's our pivot row, and the pivot value is 2. So we're going to divide everything in this row by 2. So I'll just write down here row 2 divided by 2. So that's going to give us these values: 1, negative 3 over 2, a half, 0, negative a half, 0, a half, 0, 0, 5 over 2. So this is our new row 2. So I want to get these coefficients here as 0. So I'm just going to take away from the old row 1. I'll just take away row 2. Row 3, I've got a 1 here, so I'll just take away row 2. So row 3 will take away row 2. And then here we're going to add 3 lots of row 2. So row 4, the old row 4, we add 3 lots of the new row 2. Now when we do those row operations, we will get 0, 5 over 2, 3 over 2, 1, a half, 0, negative a half, 0, 0, and a value of 11 over 2. In row 3, when we take away row 2, we will get 0, 5 over 2, negative a half, 0, a half, negative 1, negative a half, 1, 0, and then 15 over 2. And then the bottom row here, again, once we've done our row operations, we will have 0, negative 5 over 2, a half, 0, negative a half, 1, 3 over 2, 0, 1, and then negative 15 over 2 here. So notice we still got negatives here. We go for the most negative to find our pivot column, which is going to be this column here. We'll do the divisions to work out which is our pivot row. So 11 over 2 divided by 5 over 2 is going to give us 11 over 5. The next row is going to give us a negative, so we won't even consider that. And then 15 over 2 divided by 5 over 2 is going to give us 3. Now 11 over 5 is the same as 2 1/5. So this is our smallest value here. So that means that our pivot is going to be the 5/2. So we'll start by dividing everything in this row by 5/2. So row 1 divide by 5/2. That will give us these values for row 1, 0, 1, 3/5, 2/5, 1/5, 0, -1/5, 0, 0, and a value of 11/5. So this now is our new row 1. For our row operations, for row 2, we're going to take the old row 2 and add 3/2 lots of R1 because of the negative 3/2. Then for row 3, we'll take the old row 3 and then we'll subtract 5/2 lots of row 1, so minus 5/2 lots of row 1. And for row 4, for the old row 4, what we will do is we will add 5/2 lots of row 1. So add 5/2 lots of row 1. So once those values have been calculated, we'll get the following: 1, 0, 7/5, 3/5, -1/5, 0, 1/5, 0, 0, 29/5. For row 3, we will get 0, 0, -2, -1, 0, -1, 0, 1, 0, and 2. And for the bottom row, we will get 0, 0, 2, 1, 0, 1, 1, 0, 1, and -2. Now notice there are no more negatives in the bottom row, so at this point we'd normally say, right, we've found an optimal solution, or we've optimized our objective function. But notice that the value of I is negative. Now when the value of I is negative, when we've got no other negatives in the bottom row, it means that there is no feasible solution. So what we'll do, we'll just clear some space over here and we'll write that down in words. So we'll just put that in words. Since there are no negatives in the bottom row, as you can see here, of the table, we have completed the simplex algorithm. The value of I, if we read it from the table, is -2, and we know that unless I is 0, there's no solution. Therefore, the programming problem has no feasible solution. So you should now be able to complete exercise 7D on page 204 of the textbook.